Okay, hello all. Today we're going to be looking at the antiderivative and some fundamental theorem of calculus. So in this particular episode, we're going to be looking at a parabolic graph of the f of x equals x squared. No doubt you've encountered it before, and it's obviously a quadratic. Today we're going to look at how we can actually find the area under the curve between 0 and 1. Just a little bit of immersion into this new topic of integral calculus. So today's lesson will be quite basic, but it's mainly conceptual. Just getting your head around this concept of the antiderivative. Hopefully you're familiar with the derivative already and have done some differential calculus. And also this idea of what the antiderivative does and what we can actually get from it. So, let's start off with this problem that's up on the board here. So it's asking us to find the antiderivative of this parabola, x squared. And hence find the area bounding the x-axis and the graph over the interval 0 to 1. So as you can see, it's that little shaded patch there between the x-axis and the graph. Okay, so in order to do this, we know that our function is f of x equals x squared, and a little trick with differentiating polynomials, if we ever need to, or should I say integrating polynomials, sorry, but if we have something in the form of, let's say, x to the n, which is what we have here, then when we integrate it, we'll end up with having x to the n plus 1, and then we'll have that over n plus 1 itself. So if you can remember that, and obviously you could probably potentially even have an a term in there, but I'll cover that in a later video. But if you can remember that, you know how to integrate a term like this. And again, it's just like differentiation. If we had like a plus x to the 3 there, we'd just apply the same process to that x to the n. Because again, it's sort of like the sum rule if you've done differential calculus before. So now that we've got that, we can go ahead using this rule and actually find the antiderivative. So we're going the other way. Instead of going forward and differentiating to find the first derivative and then differentiating to find the second derivative, we're going backward. And that's the process of integrating and also the antiderivative. So from what we get from this is once we integrate it, we know that the f, and generally we use capital F to show that it's been integrated, but we say that the capital F of x is equal to, obviously, x to the 3 over 3, because we apply that power rule which we have with integral calculus. Of course, there's a power rule with differential calculus. This is a power rule for integral calculus. And now from this, there's another law that we use to find the area. So in order to represent that we want to find the area, we generally use an integral, and we'd have the a term of 0 and b term of 1. So you've probably seen it in its general form before, the integral having a and b there. Well, a is essentially our first little point on the x-axis and b is the second one, but so in this case we would actually have 0 and 1. I'll go through that later in another video as well, but we've got 0 and 1 there, and we want to find the area, so it's the integral of x squared with respect to x. Of course, we always need to give respect to x because that's our independent variable in this case, or the variable that we want to survey to find the area under the curve. So now from this, we can say that the capital F of 1, take the capital F of 0, which would be, if we were to substitute 1 in there, and if we were to substitute 0 in there, would equal the area under the curve, which is given by that as well. So we can say that that integral equals that there. So now when we do so, let's put 1 in here. We have 1 to the power of 3, and 1 to the power of 3 is obviously 1 itself, so the f of 1 equals 1/3, because it's going to be 1 times 1 times 1 over 3, and we also know that the f of 0 will equal 0, because from this scenario here we can see that if we have 0 in there, 0 times 0 times 0 is obviously going to be 0, and 0 divided by 3 is of course still going to be 0. So we know hence that the area under the curve will be equal to 1/3 take 0, which is 1/3 units squared. And again, we give units squared because that's what we're working with in terms of area. We generally work with squared values, two-dimensional values. So that's just a brief look at antiderivatives and also the area under the curve. A few basic things to do with the quadratic there and the polynomial. The simple rule I had up before regarding how to differentiate a polynomial, not differentiate actually, find the antiderivative of a polynomial term. That comes in handy later on. But yeah, it's quite an interesting little application of using integral calculus, and I think it's a good way to start off the unit. So hopefully you've been able to follow along with this, but again, it's just a matter of learning a few new rules, as it was with differential calculus, and applying them to different contexts. Again, we've gone forward using differentiation, now we're going backward using integral calculus. So thank you, and I look forward to continuing this module with you.